Hello everyone, welcome to ECCV tutorial from HPO to NAS, Automated Deep Learning. I'm Zhang, an applied scientist from Amazon. I'm co-organizing this tutorial with Lingjie Yang, Peizhao Zhang, Matthias Sieger, Mi Zhang, Haotian Tang, Zhijian Liu, Song Han. Why we want to hold the tutorial for automated deep learning? Researchers spend tremendous time in optimizing hyperparameters and tweaking architectures. For this tutorial, we want to encourage the researchers to design the hyperparameter ranges and possible network architecture combinations and pass the workload to the machines so that they can focus on more innovative area. So we have held the first tutorial at CVPR 2020. Let's quickly catch up what have been covered. Dr. Cedric gave us a talk on AutoML background, and I have given introduction to AutoML toolkit, which includes advanced HPO algorithms and easy-to-use Python API to quickly prototype the research ideas. Dr. Song Han gave a talk on state-of-the-art NAS algorithm, once-for-all network, and we also have follow-up hands-on section to reproduce those state-of-the-art algorithms. And feel free to check out to our previous website for more detail. In this tutorial, we will focus on the topic of neural architecture search. So let's first see what problem does NAS algorithm solves. And given an architecture space, we want to find an architecture that maximizes the reward with the network width trained to minimize the training loss on the training dataset. So in this equation, A is the architecture, W is the network width, and R is the reward, which can be accuracy or a trade-off between accuracy and latency or network complexity. So you may think of trying out all the architecture choices to find the best one. But this is not feasible in reality due to having limited computation resources and budget. Then how to tackle NAS become a challenging problem. In early work, RNN or LSTM controller is often learned to predict the network architectures, that is a series of operator choices. During the training, the controller iteratively samples a set of promising architectures, which are then trained and evaluated on the target dataset. And the resulting rewards can be used to update the controller weights using reinforcement learning algorithm. So the reinforcement learning-based approach allows us to train a small subset of the network configurations so that we can have enough information to get a reasonably good architecture that is close to the best choice. However, training each sampled architecture on the target dataset is still very expensive. To avoid retraining network weights for each architecture, many recent work allows weight sharing across different architectures. One way to achieve weight sharing is use differentiable architecture search. Instead of regarding each operator type as a one-hot selection from the operator candidates, each edge can be a soft combination of those operators, and the mixture weights are given by a softmax of the architecture parameters. This allows training architecture parameters end-to-end using gradient descent, where the loss with respect to the architecture parameters are calculated on a hold-off validation set. In this way, the objective for NAS become a relaxed version, and we no longer maximize the expectation of the reward for the architecture, but we are maximizing the reward of the expectation of the architecture. So this leads to a problem that the network passes learns to somehow coexist with the other passes in this like the super graph. So that we use the learned best architecture that may not be the optimal solution. So many recent work focus on solving this problem. Another way of tackling NAS problem is constructing a supernet containing all the network weights from different architecture choices, and learn a controller to sample from the supernet to form a subnet architecture graph. And the supernet weights and the controller weights are iteratively updated. So the objective function is still maximizing the expectation of the reward with the architecture sample from the controller, but the network weights are actually shared across different architecture choices. So it's also a relaxed version of the original NAS problem. So as a result, we often need to retrain the network weights after discovering the best architecture. So several recent work has addressed this issue that avoid retraining after the search process. That's a brief overview on different ways of tackling NAS problem. Now let our speakers to share more recent progress on neural architecture search and dive deep into state-of-the-art algorithms. Dr. Lin Jieyang will first give a general introduction on neural architecture search for computer vision. Dr. Peizhao Zhang will talk about hardware-aware deep neural architecture search. Dr. Matthias Seeger will share his recent work, model-based asynchronous hyperparameter and neural architecture search. Dr. Mi Zhang's topic is, does unsupervised architecture representation learning help neural architecture search? And the last talk is given by Hao Tiantang on AutoML for 3D deep learning.